For thousands of years, humanity has gazed at the night sky and asked two profound questions that sit at the intersection of science, philosophy, and existence itself. Does the universe have a purpose? And where did it all come from? These questions have driven some of the greatest minds in history to develop theories that have fundamentally changed our understanding of reality. The story of understanding our universe's origin begins in the early 20th century with Albert Einstein. In 1915, Einstein completed his general theory of relativity, which provided a mathematical framework for understanding gravity and the structure of space-time itself. When Einstein first applied his equations to the universe as a whole in 1917, he made a startling discovery. His equations predicted that the universe should either be expanding or contracting. Einstein, like most scientists of his era, believed the universe was static and eternal, so he introduced the cosmological constant, a mathematical term he added to his equations to counteract gravity and keep the universe stable. This fix would prove to be premature. In 1922, Russian physicist Alexander Friedmann demonstrated that Einstein's equations naturally described a dynamic, evolving universe. Friedmann showed that depending on various factors, the universe could expand from a point, contract back to a singularity, or undergo cycles of expansion and contraction. His mathematical solutions, now called the Friedmann equations, laid the foundation for all modern cosmological models. The real breakthrough came from an unexpected source: Georges Lemaitre, a Belgian physicist and Catholic priest. In 1927, Lemaitre independently derived solutions to Einstein's equations and proposed something revolutionary. The universe was expanding. He argued that if the universe is expanding now, it must have been smaller in the past. Extrapolating backward, he reasoned that the universe originated from what he called a primeval atom, an extremely dense state from which all matter emerged in a cosmic explosion. Lemaitre's theory received crucial observational support from Edwin Hubble. In 1929, using the powerful telescope at Mount Wilson Observatory, Hubble discovered that distant galaxies were moving away from us, and the farther away they were, the faster they receded. This redshift of galaxies provided direct evidence for cosmic expansion. The relationship between a galaxy's distance and its recession velocity became known as Hubble's law, confirming that the universe was indeed expanding as Lemaitre had predicted. Einstein initially resisted these ideas, but in 1931, after visiting Hubble in California, he finally accepted that the universe was expanding and abandoned his static model. The theory that would eventually be called the Big Bang, a term actually coined dismissively by physicist Fred Hoyle, proposed that approximately 13.8 billion years ago, the universe began from an extremely hot, dense state and has been expanding and cooling ever since. Not all scientists immediately embraced the Big Bang. From the 1940s to the 1960s, the astrophysical community was divided between supporters of the Big Bang and proponents of the steady-state theory. Fred Hoyle, Hermann Bondi, and Thomas Gold proposed in 1948 that while the universe expands, it maintains a constant average density through continuous creation of matter. In their model, the universe had no beginning and no end. It was eternal and unchanging on the largest scales. The steady-state theory appealed to many because it avoided the philosophical complications of a cosmic beginning. Hoyle, a committed atheist, found the idea of a creation event too reminiscent of religious doctrine. However, observations throughout the 1950s and 1960s, particularly the discovery of the cosmic microwave background radiation, increasingly favored the Big Bang model. The steady-state theory was eventually abandoned by most cosmologists. While the Big Bang theory successfully explained many observations, it left fundamental questions unanswered. In 1980, physicist Alan Guth proposed a revolutionary extension called cosmic inflation. Guth suggested that in the first fraction of a second after the Big Bang, between 10 to the minus 35 and 10 to the minus 33 seconds, the universe underwent an extraordinarily rapid exponential expansion. Inflation solved several puzzles, including why the universe appears so uniform in all directions and why it is geometrically flat. The inflationary epoch would have stretched a tiny quantum region into the vast cosmos we observe today, smoothing out any initial irregularities. Guth's theory was refined by Andre Linde, Paul Steinhardt, and Andreas Albrecht, who developed models of chaotic inflation and eternal inflation. Linde's chaotic inflation theory, proposed in 1986, suggested that inflation could begin at different points in space given the right conditions. His theory of eternal chaotic inflation went further, proposing that inflation never completely ends but continues in different regions, eternally spawning new universes in a vast multiverse. According to this scenario, quantum fluctuations drive inflation in various regions of space-time, each potentially with different physical laws. Perhaps the most radical attempt to understand the universe's origin came from Stephen Hawking and James Hartle. In 1983, they proposed the no-boundary wave function of the universe. Their idea was audacious. The universe has no initial boundary or beginning in the conventional sense. Using quantum mechanics applied to the geometry of space-time itself, they described the universe as having the shape of a shuttlecock, smoothly expanding from a point of zero size without any discontinuity or singularity. According to Hawking, asking what came before the Big Bang is meaningless in this framework, just as asking what lies south of the South Pole has no answer. The no-boundary proposal suggested that time itself emerged with the universe, eliminating the need for a first cause or external creator. While controversial and still debated, this approach represented a profound attempt to use quantum physics to address the ultimate origin question. More recently, Roger Penrose, the 2020 Nobel laureate in physics, proposed an alternative called conformal cyclic cosmology. Penrose's theory suggests the universe undergoes infinite cycles, with each cycle beginning with a Big Bang and ending in a state of maximum expansion and the heat death. In this model, the far future of one cosmic epoch becomes the Big Bang of the next, creating an eternal sequence of universes. String theory and M theory, which attempt to unify quantum mechanics with gravity, also predict multiple universes. These theories require additional spatial dimensions beyond the familiar three and suggest that our universe might be one of countless others in a vast multiverse landscape. In these scenarios, different universes could have different physical constants and laws, dramatically changing our conception of cosmic uniqueness. The question of cosmic purpose has ancient roots. The concept of teleology, the idea that things exist for specific purposes or goals, originated with Greek philosophers Plato and Aristotle in the 4th century BCE. Plato viewed the universe as crafted by a divine demiurge, a rational agent, who arranged the cosmos according to eternal forms to produce good effects. Aristotle developed the notion of final causes, arguing that everything in nature has an inherent purpose or telos that can be discovered through observation. During the medieval period, theologian Thomas Aquinas integrated Aristotelian teleology with Christian theology. Aquinas argued that the universe's intelligible order must ultimately come from an intelligent source, God, who is the final cause and purpose of all things. This teleological worldview dominated Western thought for centuries. The scientific revolution of the 16th and 17th centuries challenged teleological explanations. Scientists increasingly sought mechanistic causes, the how of phenomena rather than the why. The new emphasis on mathematical laws and efficient causes made purposeful explanations seem unnecessary or unscientific. The universe came to be seen as a vast machine operating according to impersonal physical laws rather than divine intentions. However, the question of purpose never completely disappeared. In the 18th century, philosopher William Paley formulated the famous watchmaker argument, claiming that the complexity and apparent design in nature pointed to an intelligent designer, just as finding a watch implies a watchmaker. While Charles Darwin's theory of evolution by natural selection later provided a mechanistic explanation for biological complexity, questions about cosmic fine-tuning would revive teleological debates in the 20th century. In 1974, physicist Brandon Carter introduced the anthropic principle to address a remarkable observation. The universe appears exquisitely fine-tuned to permit the existence of complex structures and life. Carter distinguished between two versions: the weak anthropic principle, which simply acknowledges that we can only observe a universe compatible with our existence, and the strong anthropic principle, which suggests the universe must have properties that allow life to develop. The apparent fine-tuning is striking. Physicist Martin Rees, in his book Just Six Numbers, identified 6 fundamental constants that appear precisely calibrated to allow for stars, galaxies, and ultimately life. If the strength of gravity, the cosmological constant, the nuclear fusion efficiency, or other fundamental parameters were even slightly different, the universe would be radically different, perhaps entirely sterile. Physicist Paul Davies has extensively explored these questions. He notes that the universe's physical constants seem to occupy an incredibly narrow range that permits complexity and life. Davies writes, that the universe appears to be fine-tuned for the building blocks and environments that life requires. This observation has led to intense philosophical and scientific debate about whether this fine-tuning implies design, purpose, or simply observational selection. Scientists and philosophers have proposed several explanations for apparent cosmic fine-tuning. The multiverse hypothesis suggests that if countless universes exist with varying physical constants, it's not surprising that at least one, ours, has the right conditions for life. In this view, we exist in a life-permitting universe, not because of design or purpose, but because we could only arise in such a universe, an observational selection effect. Others argue that a more fundamental theory of physics might reveal that the constants are not arbitrary, but necessarily take the values we observe. String theory and other approaches seek such deeper explanations. Some physicists maintain that the apparent fine-tuning is simply a reflection of our incomplete understanding. The development of quantum mechanics in the early 20th century added another dimension to these questions. Werner Heisenberg's uncertainty principle, formulated in 1927, revealed fundamental limits to what can be simultaneously known about quantum systems. Max Planck's quantum hypothesis, introduced in 1900 to explain blackbody radiation, showed that energy comes in discrete packets rather than continuous amounts. Niels Bohr's complementarity principle emphasized that quantum phenomena cannot be understood through a single classical picture, but require multiple complementary descriptions. These quantum principles suggest that at the most fundamental level, the universe operates according to probabilities rather than certainties. Quantum fluctuations, temporary variations in energy allowed by Heisenberg's uncertainty principle, can have macroscopic consequences. Some cosmologists, including Alan Guth and Andre Linde, propose that quantum fluctuations in a primordial vacuum could have triggered inflation, ultimately giving rise to the entire observable universe. If the universe emerged from quantum randomness, what does this imply about cosmic purpose? Contemporary scientists and philosophers hold diverse views on cosmic purpose. Some, like physicist Stephen Hawking, argued that the universe requires no external purpose or creator. It simply exists according to physical laws that can be understood through science. Others, like Paul Davies, suggest that the universe's apparent purposefulness or meaningfulness might be inherent within its structure, discernible through scientific inquiry itself. The philosopher and mathematician Alfred North Whitehead proposed that purpose might emerge in the universe rather than being imposed from outside. Similarly, 19th century philosophers Georg Hegel and Friedrich Schelling envisioned the universe as a self-organizing system, developing through stages toward greater complexity and consciousness. These ideas resonate with modern observations of cosmic evolution, from simple hydrogen to complex structures like galaxies, stars, planets, and living organisms. Some scientists maintain a clear distinction between scientific questions about mechanism and philosophical questions about meaning. The universe's physical laws can be investigated and understood without invoking purpose, yet individuals may still find personal meaning in existence. Others argue that the extraordinary improbability of a life-permitting universe demands explanation, whether through multiverse theories, fundamental physical necessity, or design. After a century of revolutionary discoveries, we understand far more about the universe's origin than ever before. The Big Bang Theory, supported by multiple lines of evidence including cosmic expansion, the cosmic microwave background, and the abundance of light elements, provides a coherent account of cosmic history from the first fraction of a second onward. Inflation theory explains the universe's large-scale properties, while quantum mechanics offers insights into the earliest moments. Yet profound mysteries remain. What, if anything, existed before the Big Bang? Why do the physical constants have the values they do? Is our universe unique, or one among countless others? And does the cosmos have meaning or purpose beyond the mechanistic unfolding of physical laws? These questions may never have definitive scientific answers. They touch on the boundaries where science, philosophy, and perhaps faith intersect. What we can say is that the universe, as revealed by modern science, is far stranger and more wonderful than anyone imagined. Vast beyond comprehension, ancient beyond reckoning, governed by quantum uncertainty, yet displaying elegant mathematical order, apparently fine-tuned for complexity, yet possibly just one universe among infinite variations. Whether the universe has purpose remains an open question, one that each generation must grapple with anew in light of expanding knowledge. What is certain is that humanity's quest to understand our cosmic origins and place in the universe represents one of our species' most noble endeavors.